Hi, what I have here today on the bench is an Extech 380/460 milliohm meter, which is my latest eBay purchase. I wouldn't have bought it if it was not for the price tag, as I already have meters that are capable of doing accurate milliohm measurements. For instance, my Keithley 196 bench meter. But this meter came with a whole package, including the meter itself and the Kelvin leads. So I thought that at the very least, just the leads themselves would easily justify the purchase. By the way, I think I paid a total of just under $60 on the whole thing. So I think it's a pretty good deal, and that was including shipping as well. And a brand new 380/460 would set you back around $300, as this is still a current production model. So anyway, as you can see, this unit actually looks pretty much unused. The protection film on top of the instrument has not even been peeled off yet, so I'm not really sure what the real deal is as to why it was auctioned off. But again, government agencies and universities on grants routinely sell off their old equipment as they get new fundings for new purchases. It is certainly a waste of taxpayers' money, but definitely a bonus for the hobbyists. So as for the 380/460, it has a very rugged case, and it was clearly designed for field use, for electricians. But it does need to be plugged into the wall power outlet, so it is not really that portable. And before we open it up and take a look at what is inside, the construction of the whole meter, let's power it up and take a few measurements to see how it compares with my Keithley 196. So let's take a look at the specification briefly. For this Extech meter, the 200 milliohm range is measured at a resolution of 0.1 milliohm at a current of 100 milliamp. So this test current is considerably higher than most of the multimeters. And even at 2 ohm to 20 ohms, and the test currents are at around 10 milliamps. So the accuracy is specified at 0.75% plus 2 digits or 4 digits. And this specification compared to our Keithley 196. So I just printed out the spec for Keithley 196. And you can see that Keithley 196 on paper actually is much a higher range than the Extech meter, because we can measure up to 300 ohms at a resolution of 0.1 milliohm. But as you can see here, the current is only at 1.7 milliamp. So now let me plug in the power and we can do some measurement. And from the back here, you can see that we have this power input. I'm going to plug the power in. And also we have this 4 Kelvin leads sockets. And the 2 outer ones are marked with high and low. These are for providing the current to the measurements, and the inner 2 are for your voltage measurements. And your Kelvin leads, here we have the, you can see these bands on the leads themselves. They are actually helping you to determine which leads are plugged in where. So typically, at least according to the manual for this meter, is that the leads marked with a white band are for the sensing. So let's plug them in. And like so. And let's do some measurement here. By the way, so the first thing I noticed is that these leads are not really well made. I mean, these they feel very, very loose, and the tension is actually being applied by these 2 rubber, looks like a rubber band on this tip. And because these cannot make electric contact while you are in use, that's why they have this kind of construction using this kind of plastic separator to separate out the 2 leads. But the tension really is not there, so you're going to have some issues when you are trying to connect to things securely. Also, another thing is that these leads, if you notice that they are actually just heat shrinked onto the the actual clip. And over time, they're going to be kind of, when you bend them back and forth, they will come loose. And actually, I think this one might even be a little bit loose. I can kind of cut it open later and see if I can make the connection again. But for now, let's move on to the testing, and we'll worry about this later. So for that, let's turn it on. And right now we're in this 200 milliohm range, and you can see that we have a separate range for 200 milliohm, and the other end we have from 2 ohm all the way up to 2K. So right now let's concentrate on the 200 milliohm, and let's zero it out. So let me hook it up like so, and we're not making any contact, it doesn't seem. So that probably is some issue with the leads here. So it looks like the leads are actually not connected. That's okay, so that's probably the reason they're selling this. Now let's wiggle this. Oh, okay, so I got it. So this one actually is not connected correctly. Well, right now we cannot use these clips, but I do have some clips I made. I think we can use that to do the measurement, and we'll fix this later. And unfortunately, we cannot use this leads. So I do have some rather crude Kelvin leads, and these are the ones I bought the clips on eBay, and I can use those instead. Okay, so these are the low, and let's just get this polarity straight, even though it doesn't really matter. So let's see. So now, of course, the performance we see going to be slightly different than the lead supplied with, but we can get a point here. So let's zero it out. I actually prefer these leads much better because the tension is much greater than the leads that you saw earlier. And for that, we're going to adjust it to 0. Okay, so now for the first measurement, we have this 0.1 ohm, 1% diode resistor. So this is a precision resistor, and with a tolerance of 1%. So let's take a look at what the reading is. And we're reading 98.8, so slightly out of the tolerance, but it's nevertheless pretty close. So let's again make sure that we are zeroed out. Okay. So that's the first resistor, and the second one we wanted to attempt to measure is this shunt resistor. This one is actually a little bit tricky. It's marked as a 50 amp 75 millivolt. So which means this whole resistor, this shunt, only has about 1.5 milliohm resistance. So let's see if we can measure that successfully. And because of the leads here are a little bit small, so I don't really have a good place to clip them on, so I have to hold them in place. So let's do that. Not bad. So as you can see from the reading, it's a 1.5, 1.6. So that is working correctly. And the last measurement I want to do before we open this up is to measure this 5 watt 10 ohm resistor. So for that, I'm going to switch the range to the 2 ohm to 2K range and put that to 20 ohm. So let's take a look. And it's reading 10 ohm, sorry, so no problem at all. So just for curiosity, let me compare the result to the readings from my Keithley 196. So let's do the same measurements using this Keithley 196 precision bench meter, and to see what the measurement we get. For that, I also hooked up these Kelvin sensing terminals, and let's give it a go. So I'm going to switch it to milliohm range. Let's see, ohm. Actually, it only has ohm range, but let's go all the way down to ohm. So the main difference, while I'm zeroing it out, let me explain here. So the main difference between this Keithley 196 and the Extech we saw earlier is that this one is a precision instrument that is not designed specifically for the milliohm measurement. So the current that it uses is actually quite low. It's only a couple of milliamps. Whereas in the Extech scenario, we are using about 100 milliamp to measure the resistance. So the noise level of this Keithley 196 is going to be much higher because of the low voltage reading from the probe due to the low current. So nevertheless, let's give it a try, and for that I'm going to zero it out. So the first we're going to measure this again 0.1 ohm 1% diode resistor, and let's see what the reading is. And it's not quite 0.1 ohm, and as you can see, it's very sensitive to how the clips are applied. That's because of the low current and the low voltage from the measurement. So as you can see, we're not able to read it very accurately, and so I suspect the same would be for this current shunt, as this is only 1.5 milliohm, but we can give it a try. So for that, I'm going to clip it on and hold it. So when I apply enough pressure, surprisingly enough, it is actually reading pretty well. Well, it's shifting quite a bit, but you can see it did register around 10, 15, 14 milliohm, but that clearly is not good enough because you can't rely on that reading. So we can see that even for this precision instrument, you cannot beat a dedicated milliohm meter in terms of milliohm measurement. Anyway, so now let's go ahead and open up that Extech meter and see what's inside. So let's take a look, and I think I have to remove all the bottom screws. Not sure what these two are. Let's I'm not sure what these compartments are for, so let's take a look here. And interesting. Not entirely sure what this compartment is, but we can keep opening it up and see. Okay, so now all the screws are removed. I'm going to try to open it up. And here we go. So the first thing you notice is that this is a single board design, and the layout back here is actually okay. Unfortunately, we can't see anything from this side, so I have to take the whole thing out. And to take this out, actually, I have to pop off these two knobs, and I think now I need to actually unscrew these standoffs, because these are double standoffs, so one side is actually connecting the bottom. So let's remove these. Okay, here we go. And we are Now we can review the bottom of the construction. What is annoying is that we don't have dedicated connectors for these things. They are just soldered right in place. So unfortunately, I can't totally remove these without desoldering these wires. But nevertheless, we have enough we can look at what is going on here. The first thing is that we have this transformer here, and the AC comes in here, going through this fuse. So if you need to replace the fuse, you have to open the whole thing up. But that is probably least of your concern. So let's see, we have a regulator here that is a 79, or is that 79? Yes, so there's a 7905, and we have a 7805. So these two provides a plus and minus 5 volts supply. And I just pried off this LCD display so we can have a better look. This is actually very interesting. The original LCD, you can see that comes in, it's a slightly, the pin pitch, actually the pin pitch is exactly the same. So I'm not sure why they don't, okay, so I see now, because the pins are a little bit shorter here, so they actually use this riser board to put another set of a pin header, and so you can plug it onto the main board. I suppose that's better than just soldering them down so that you can change them later on. So that's, I suppose, is a good approach. And so surprisingly, the board is actually surprisingly Spartan. And as you can see, the most of the logic happening here are done totally, entirely analog. That is a dead giveaway by the number of trim pots here. So you do not want to touch any of the trim pots, as the price you pay for this kind of instrument, especially for this one, as you can see, the material cost is relatively low. And the price you pay is actually for the calibration. So if you touch any of these, the calibration is out of the window. So don't touch these. But from the construction here, we can see this is a 7106 CPL, which is a very popular 3.5 digit AD converter. So this is the only digital portion of the circuitry. The analog signal comes in, and then this one converts it to the 3.5 digit that you see on the LCD. So this one is doing the conversion and driving the LCD at the same time. And other than this, the entire circuitry, as I mentioned just a bit earlier, is analog. The mechanical switch here is for your power. As you can see, the 120 comes in to the switch, physical switch, and it goes to the transformer. And it would be nice if they have a connector here so we can disconnect that when we're looking at the board. But there is a little bit of flux residue for these fuse holders, not a major problem. So the regulators here you see are these two standard 7879 series regulator, and one is for negative 5 volts and this one is for positive 5 volts. Interestingly, these are not tied down by any means. These are actually just let me show you. These are just floating above the circuit board. And especially for these kind of things designed for rugged use, these would cause long-term reliability problem because you don't tie it down, it keeps shaking and it could come loose one day, and that would cause the failure. And here, these are just some diode bridge rectifiers for the voltage regulation. So nothing major here. And what we see here, this chip is actually just a 741, so it's a op-amp. It's a 741 variant. And the only precision part I see here is this op-amp. This is a Texas Instruments OP070. So that's actually a very low offset voltage op amp, precision op amp. So that clearly is needed for the voltage source, for the current source and voltage measurement. So how this kind of a meter works is basically it has a precision current source, and then at the other end you have a precision voltage measurement. So to read out the voltage, and all these trim pots are presumably for trimming the voltage reading, linearity, and your current. So the entire meter is actually surprisingly simple, and given that it's mainly an analog device. From the date code here, you can see this meter was actually made a long time ago, was 2002. And it does have a Lutron stamp all over the place. I'm not sure if it's that company made the board or just some components, because they do provide transformers and components like that. So that's pretty much what I expected to be inside this Milliohm meter. And here one more time is the LCD display. And from the timestamp, you can see that this LCD was made back in 1994. So this unit is actually over 20 years old. I'm actually surprised that the same model is still in production. Anyway, time to put this back together. And here's what happened to that Kelvin lead. As you can see, this actually just broke right off. So this construction actually is not very thought out well, because during use your hand going to be putting pressure on these ends, and over time, this heat shrinking tube is not going to be strong enough to hold this leads in place, so they're going to gradually break off. And what I'm going to do is I'm just going to solder it right back, and we should be good to go. Anyway, I hope you enjoyed this teardown video, and if you liked the video, please give it a big thumbs up, and do remember to share and subscribe. I will catch up with you next time.